This is further stats 2 from 2024. First question is about regression, as it usually is. We look in the formula book, we find this. If we've got SWW, so if we're trying to find B and A, which is what we're trying to do here, um, the W's must be behaving as the X's if we're going to make this work straight away. So let's make a mental note that W is essentially behaving like X, and then we can just do this one over this one to find B. And then, of course, from this formula here, again, if the W's are behaving like X, that means W bar, which is, of course, this divided by whatever N is, which I think is 10. That's going to be the one that goes to there, and then the V is going to be the one that becomes the Y. So, of course, we can shove those three results that we've got into there, and we can find A as this. And then the line of regression is just this with V and W. Again, W behaving like the X, I guess, in this equation here. And then, of course, if W is what, T minus 40, and then, sorry, V is T minus 40 and W is root H, put those in, add 40 to both sides, and that'll be that done. And then it says that the water level for height of 9 is, or to fall a height of 9 is 47 seconds. Okay, so let's put the height of 9 in here, and let's use this regression line to work out what it predicts the time should be. And it predicts the time should be 46.16 seconds. So if we imagine drawing this as a picture like this is the regression line here. It's predicting 46.16, slightly lower than what it actually took. So this is the actual point plotted here. Of course, the residual is just the difference, the straight line difference down. Actually, it's the distance across, isn't it? But it doesn't really matter. It's the distance between the point and the line there. No, it is the straight line distance, isn't it? It is the straight line distance down to the line, just the residual, the difference in the y coordinate. So therefore, it's just this minus or this minus this, which is going to be this as our answer, very roughly. Anyway, and then it says calculate RSS for this model here. Well, of course, we can look up the RSS. It says it's the same for T and root H as V and W, so we may as well just use the V's and W's for this. Of course, the W's are this one still, so we need SVV, but we can work out SVV by using this formula, which is down here. I mean, any of these is fine. It's just this second one over here that we need using these sum of V squared and sum of V ideas. So SVV is going to be this, then we can use that in here with all the other numbers that we're given, and we can work out RSS. Is that there? Student B models data with this, and their RSS is 980. Now, their RSS is much bigger than this one here. So if the residual sum of squares is bigger, then it's a worse model. So B's is a less suitable model. And that's all we have to say there. For question 2, then, the Spearman's rank question. It's kind of confusing that they put in rank here. This has nothing to do with ranking by Spearman's. This is just because they were asked to rank things themselves. Okay, you could put the difference down below here and just say, well, what's, if A is the first letter and E is the fifth letter, that means there's a difference of 4 between them. Or you can get out a new table and actually, title it with the things that they're ranking, and then say, well, number 1 ranked A at 1, and then it ranked B at 6, and so on. And you can make the table like this, and then you can work out the differences. But again, if you know where the letters are in the alphabet, you could just write them underneath here. But anyway, these are all the differences between those things. And then, of course, we just use the formula in the formula book. 1 minus 6 times the sum of d squared. So d squared, or the sum of d squared is 4 squared plus 1 squared plus 1 squared plus 1 squared plus 2 squared plus 1 squared, which is this. And then n is just 7, it looks like. So we just plug that in, and we get r as this. So that's A. And then stating your hypothesis. So, of course, h0 is rho equals 0. H1 is rho greater than 0, because it says whether or not to are in agreement. So we want some positive correlation, essentially, between them, I guess. Or association between them, maybe. Look at the Spearman's coefficient. Of course, sample size is 7. We want, it's a one-tailed test, 5%, so that's 0.05, so that's this box here. Our number is less than that, so we're not in the critical region, so we'll accept H0. And then we'll always write something in FS2 and FS1, always write something contextual at the end of every single hypothesis test. So something about customers ranking the house. Always just write something. Otherwise, you may well lose a mark, and it's not worth losing a mark just because you couldn't be bothered to write a sentence. Question 3 then, so we're doing a confidence interval. Bear in mind there's very little about confidence intervals in the formula book. So this is definitely something you'll need to have memorized, I think. So this is the general way of just making a confidence interval when you're given basically all the information, which we are, or a confidence interval from a sample. I think this is really what this is, when that sample is normally distributed, or the original thing is normally distributed. Okay, we look up the Z value for a 90%. It's, of course, 2 ways, because confidence intervals have to be one at the end, at the lower end, one at the upper end. So that's going to be, of course, 10%, but halve it down to 5%. So we're looking for this one here. So that's the value we need. We're going to put that into there. X bar is, of course, just the mean of the sample, and sigma is this sigma, and n is the sample size. And then we do 30 plus this thing, and then 30 minus this thing, and that gives us either end of the confidence interval there. Good. And then a suitable test is carried out to work out whether there's not any evidence of variance. Now, again, this is a very specific thing we need here, which is in the formula book, which is this. The giveaway that it's this one here is because it's asking you for s squared, and this is the thing with s squared in it. So what we're going to do is we're going to use the chi-square table to find the critical number, and then we're going to rearrange for s squared. But again, not too obvious that this is the right thing to do, other than just knowing every case and all the subtle differences between all these tests, but also just seeing this s squared here, looking for it in the formula book, and noticing that this exists here. So anyway, get out the chi-square test. There are 15 things, so 15 minus 1 is 14. So 14th row, it's a 10% test, and we're looking for whether it's increased. So that's a one tail. So 10% here. This number here is what we're looking for. And then, of course, we'll make that the critical number there. We want to be inside the critical region. So we need to be bigger than that. And then, of course, it's just 14, which is from here, times big S squared over sigma squared, sigma being this original sigma up there. And yeah, we just rearrange this for x squared by timesing that thing over there, divided by 14 and square rooting. Although we don't actually have to square root here because it says 4s squared actually. So we're going to reject h0 if this is true here. Then it says the manager has checked, but essentially he's doing both tests. He's checking for the mean and then he's checking for the variance. The mean via this confidence interval and then the variance via this statistic here. The next month it's 15 things, so of course 15 means we can use these two things because they are both based on 15 as well. The mean was this, the standard deviation was that. Now, just be careful here. The mean, of course, lies within the confidence interval, so there's no reason to reject it because of that. The standard deviation is s, so let's root this down, and the test will actually be if s is bigger than that. But s is less than that, so of course we're therefore going to not reject either one of these tests, and therefore the whole thing, because the mean's in the confidence interval, and the standard deviation is also not in the critical region. But you do need to have either squared this or rooted that for that extra mark there. For that one there. Anyway, question 4, continuous uniform distribution. So I just imagine that as a rectangle between minus 3 and 15. That width is 18. So for this area to be 1, 18 times 1/18 is going to be area 1. So I don't think that's actually going to be very important. But anyway, 12 is somewhere over here. And 12 only has a distance of 3 across there. So it's 3/18 of the whole thing. So the probability of being bigger than 12 is therefore 3/18, which is a 6. H has another rectangle over the interval 2w. And the expected value of h, which is just the average of h, is 10. So 10 must be bang in the middle of this rectangle, which means, of course, that w is 18. And yeah, the probability that it's... Okay, well, what's the probability of this being greater than 12? Well, 12 is 6 away from 18, so it's 6 sixteenths of that rectangle, because here is 6 if that's 12, and the whole thing is 16. And then, of course, if they need to be both be greater than 12, then we just do this times this, assuming they're independent, of course, which is 1/16. So that's good. I probably should have said here, this is true. You know, this is P of A and B is equal to P of A, P of B if and only if independent, which is told us, but I probably should have written that down. Anyway, the random variable A is the area given by this. Okay, let's draw this. Firstly, I'm actually going to draw this. K is another rectangle between 5 and 10, so that's height 1/5, because 5 times 1/5 is 1. And, okay, well, let's draw this now. So y equals minus 3. Just a horizontal line down here. Now, mod x is just a v shape. Times that by minus 4, and it's a steeper upside down v shape. Add k, and you're just going to move it up like this. So it's going to look a bit like this, with k being here. K is between 5 and 10, so that's up here somewhere. We know that. And what I need here, I think, is I need to work out the area of this rectangle, sorry, of this triangle here. Now, the height, if this value is minus 3, and this value of k, the height is just k plus 3. Now, the width, I would need to find the intersections between this and this. Let's do that by putting in my y as minus 3 into here. We can put this on the side and add 3 to both sides. Then we can divide by 4. And now this either means that x is just equal to this, or minus x is equal to this. In other words, x equals minus all of that. Those are the two options. So obviously this one is going to be this point, and this one is going to be this point. But that means the width across here is just the difference between these two things, which is a half k to get from a quarter to k to minus a quarter k, and I think 1.5 to get from 3/4 to minus 3/4. So that's the difference there. And now, of course, the area of the triangle is just a half times this times this, which we can work out is this. And now, if you have a function for the thing that you're trying to find the expected value of, deep in the formula book is this stuff down here, And for a function, the expected value of a function is the integral of that function times f of x, where f of x is the probability density function of the original random variable x, in our case, k. And the probability density function of k is just a fifth, because it's a uniform distribution. This line here is just y equals a fifth, or f of x equals a fifth. So we're going to use this idea here, and we're going to integrate this function here times a fifth dk, between 5 and 10, of course. And we're just going to do that integral. It's very easy to do, of course. You bring some constants out, you integrate this via reverse chain rule, which is obviously really easy. You put the numbers in, and you end up with the expected value. It's just about that. Question 5 then, another continuous random variable question. So we've got the little f of x. So the first thing I'm going to do is integrate that for big F of x to work out the commutative frequency density, which is this. Just raise this up to -1 divided by -1. Raise that up to -2 divided by half. Sorry, divide by -2 is the same as times it by half, I guess. I should have put a plus c here, but it's not going to make a difference because all I'm going to do is, now that I've got the commutative function, I can just integrate, I can just substitute in upper limit of 4, lower limit of 2, and that needs to equal 3/8, because that's what the commutative frequency function does, right? So I didn't even need to write this down, and probably shouldn't have, but the integral of little f of x between the upper bound and the lower bound is the area, and therefore the probability that you're going to have on a thing. So, of course, we just need to substitute in 4 and 2, and we get this. Now, this is going to give us an equation in A and B. The substituting isn't too bad. Just put it in. I'm going to multiply by a bunch of stuff to make it like this. Now, this obviously looks like half of a simultaneous equation. So I need the other half. Where am I getting it from? Well, if I integrate between 2 and infinity, or just input 2 and infinity into this, I should end up with 1, because the whole thing is found within this part of it. And so therefore the whole thing needs to add up to 1 because it's a probability. So yeah, that's, but of course when we input infinity, 1 over infinity is 0, and so is 1 over infinity squared, essentially. So all of that just goes to 0, the first input. If you're doing this in Corpio 1 and 2, you need to write, limit as t goes to infinity and put a t here, but I think we can get away with it here, just putting it in and just saying it's 0. I think that's fine. And of course put in 2 and you get this, and that turns into this eventually. And now if you just solve this, if you want to, you can just put it in the calculator. It's not a difficult one to solve. You get b is 4 and a is 3, which is good. Maybe show that you're working. Maybe you do need to do this. I don't think you do, though. I think you can just get to here, and that's fine. I think the working is all of this stuff. Anyway, find the exact value of the median. So I'm going to put in this result for A and B into here, and then I'm going to say if I substitute in m to 2, 2 being the lower, of course, and m being the median, I should get a half, because the median is up to halfway along. Half the data is below it, so therefore the area is a half. And now I can just input m and 2, and you end up with this times by m squared times by 2 maybe as well to get rid of everything. It all turns into this. And yeah, you can solve that in a calculator. And of course, 3 plus root 5 is the one we want, because 3 minus root 5 is less than 2, and therefore is not an answer to this. It can't be it. So it must be 3 plus root 5. And that'll be that one done as well. Okay, a 2-sample t-test won't work because these two things are not independent, because they're, each one is a twin, so therefore not independent, because we all know twins are just identical in every way and can read each other's thoughts and all that kind of thing. So yeah, not independent. So we will need a paired t-test instead, which is what we're going to do. 2 other factors. The answer book said all of these things, so apparently you just need to write a couple of things about the context of lambs being born. I don't really like these kind of questions, but whatever, those are the things that you can say, apparently. State one assumption in context that needs to be, I should say here, context is always the thing that you should just do. If you're not sure, just write something about the context of it. That seems to be the way to go in FS1, FS2. So yeah, anyway, state one assumption that needs to be made. Well, of course, we need to say that the differences, because we're about to find the differences between all these things, to do the paired t-test, the differences need to be normally distributed. You can't just write normally distributed. The differences need to be. So anyway, let's find the differences. We'll call them big W because that's what it tells us to do them. And it tells us to do this one minus this one as well. So we'll do all that, and now we can. Sorry, we need this equation here, or this formula here, to find the confidence interval. Again, I mentioned earlier that there isn't a great deal about confidence intervals in the formula book, so you just need to go in knowing these results. This one is apparently from page 168. It's the one with the t in it. Of course, they've given you a hint that that's what you're going to be doing. So yeah, this is just something you need to have memorized. X bar is, of course, the average of the W's, and S is the standard deviation of the W's. You can actually just type that list into a calculator, and find those two things very quickly. If you want to just work them out yourself, you can do. Of course, this here is the variance, so you need to root it for the s. I just couldn't be bothered to find what it actually was, so I just wrote root. Okay, and now of course we need to find the relevant t value. So, well, n is I think what, 8 here? So n minus 1 is 7, so we're looking at the 7th row, and it's going to be, it's obviously two-tailed because it's a confidence interval, so half of 2% is 1%, find 1%, find this value here. So there, that's the mean, as we said. That's the t value that we just looked up, and then s and n from there, and we go either side with the plus, with the minus, we get those two values there. The researcher believes that W is greater than 200. Now, 200 grams is 0.2 kilos. Notice we did the whole thing in kilos. So let's write the hypotheses. And the mean of the W's is 0.2, is H0, and then the researcher thinks it's greater, so that's H1. Now, use your confidence interval. Now, 0.2 is within this confidence interval. So we are going to accept H0. And then maybe we'll write some... I've broken my golden rule, haven't I? I should have said there is no evidence to support claim, and then write context about differences between the two things. There's no evidence to believe the differences is greater, the average between them from one lamb to the other when doing this whole thing. Write context. I'm not going to bother saying it again, and I couldn't be bothered to do it apparently myself, but write some context. I'm sure you can come up with a sentence that's relevant there. Anyway, we've now got our question about the e's and vars of a couple of different distributions. I like these questions quite a lot because they're nice and straightforward, I think. Firstly, this thing here we're going to say is a binomial because there's m people and probability p. So x is twiddled with the binomial, and so is y, just with n people instead of m. And so, well, okay, an unbiased estimator is when E of Q is equal to the thing that it's estimating. So in this case, P. Okay, well, E of Q, firstly, let's break this down into, with X and Y having just coefficients in front of them like this. And the reason I'm doing that is because now E of Q is E of this plus E of that. And now we can put these constants here, the coefficients, in front of the E's, like so. That's how it works with E's. And now E of X, well, for a binomial, E of X is just MP, and E of Y is just NP. So we can shove those results in there. The N's and the M's cancel, and we get 2kp. But of course, E of Q is P because it says it's unbiased. The P's cancel because P isn't 0, and we get K as a half, I guess, which is what they were asking us to do. And now we're going to do exactly the same thing with this one. So we're going to write it down. E of R is still P because it's unbiased. Write it down like this. Put the E's in, move the stuff out. Replace those with the things that I said they were before. Replace this with a P because that's what it is. Cancel the M's and the N's. Cancel the P's. And we end up with this, which is what they wanted. Given M and N is this, and R is a better estimator. Now, if R is a better estimator, that means var of R is less than var of Q. So now, of course, we need to work out var of R and var of Q. So let's do that. We're going to need the variance of X and Y first. And that's, of course, just from regular A-level stats, NP1 minus P. So we're going to need those results too first. Now, var of Q, when we do variance of things that are being scaled, that comes out at the front, but you square them as you do that. So that becomes this, and that becomes this. And now we can put the variances in, we can do some cancelling, we can do some factorizing, and we can do all that stuff, and we get this here. I'd forgotten, or actually, I didn't forget, I just didn't read this when I was doing it. So I just left this as this for now. I'm going to put it over there. And now let's do the same thing for variance of R. It's the same idea. When these things come out, they need to square, and then you replace with these things here, and then you cancel stuff out. It all becomes down here like this. Do some factorizing. And now I got a bit stuck before I actually bothered to read this. Let's put M and N in there. You get this. Do some simplifying. You get that. Do some simplifying. Maybe double this fraction out. Factorize out the 200. You get this. And now we need this thing here to be less than that thing there. So, okay, let's maybe times everything by 200. It's a positive number, so it won't affect that. P is positive, 1 minus P is positive, so let's just cancel those things out. We get this. And now B is, I think we had it earlier. Did I write it down earlier? Where did I write it earlier? Oh, sorry, there. B from here is 1 minus A. We worked out earlier. So I can replace B with 1 minus A. And now it's saying range of values for A. This is going to give us that, right? Expand this thing out. Collect everything together. Maybe times everything by 4. Factorize. 2 critical values are a sixth and a half. Want to be less than 0. It's a right way up quadratic. So therefore, between a sixth and a half will do. And that question is done as well. Question 8 then, the weight is normally distributed like this, so okay, just write that down. Standard deviation means this needs to be squared here. And sample of 3 small bags, so let's just call that x is S1 plus S2 plus S3, it's 3 samples of S, which means the mean is just the expected value of x is just E of S1 plus E of S2 plus E of S3, but all of those are 500, so therefore the expected value of x, or just the mean of x, is 1500. And likewise for the standard deviations, or the variances, each one is 25, just add them together for 75. So that's the distribution of x. We want to be between these two values, so just get out a calculator, put it in, lower limit, upper limit, root this when you put it in, I guess, and you get this thing here. Now, we've got a large bag is this and this, so let's put that down. One large bag and one small bag are chosen. Now, we want the probability the weight of the large bag is at least 30 more than twice the weight of the small bag. So we need to work out a distribution for twice the weight of the small bag. So we need to work out 2s. Now, 2s, firstly, 20 squared is 400, I guess. Now, 2s is just double the mean, but you don't just double the variance. You times it by 4 because of this rule that we've been using all day. So if we double the distribution, we actually end up taking that factor of 2 out and squaring it to times this whole thing by 4 here. So it ends up being this distribution here. Now, the reason I'm doing that is because what I want to do is I want to work out, well, I really want to write down one more distribution here, which is L minus 2s. We'll call that distribution Z. So L minus 2s will just take away the means to get, it's normally distributed with a mean of 20. But don't take away the variances, of course. Always add the variances. 400 plus 100 is 500. And now this is looking good because all we're going to be asked to do here is I want to work out that the difference between a large and twice the small is more than 30. I want the difference to be at least 30. So I want the probability that Z is more than 30, which of course is 1 minus the probability is less than 30. And with this distribution here in a calculator, we can work that out very easily. And we'll end up with that number there. Thank you for watching, and I'll see you next time.